Somewhere in the universe, something can accelerate the charged particles at the hearts of atoms so much that a single atomic nucleus can travel with the energy of a fast-pitch baseball. Now, a fast-pitch baseball is as much more massive as an atom as the Earth is compared to a baseball. So if a pitcher could accelerate a baseball as much as these charged particles in outer space have been accelerated, it would be as if the whole Earth was being pitched at the baseball bat. But if one such particle is traveling at us from across the universe, how do you detect it? One of the aspects of astronomy that I find most exciting is we must invent ways to sense things that we cannot see or hear or smell. How do we know things about the universe? You probably know that there are 8 planets, even though you've probably only personally seen Venus and Mars, and Jupiter, maybe Saturn, and Earth, of course. But we could build a telescope that collects more light than your eyes do alone, and this lets us see the faintest planets. But not all the light in the universe is visible to us, and not all the information that reaches us about things we can know about the universe arrives as rays of light. So there's literally more to the universe than what meets the eye. Charged high-energy particles, called cosmic rays, reach us from some of the most extreme environments in the universe. And so catching and understanding these particles gives us clues to interesting places and types of things that the universe can do. Let's start by imagining the kinds of places that these particles come from. When a massive star goes out after it's used all of its fuel, it can leave behind a dense core. And this innermost heart of the star can be more massive than the sun, but packed into a space the size of San Francisco. It's also spinning extremely fast and has a really large magnetic field, and this makes it a particle accelerator stronger than what we can build on Earth. The highest energy particles that we can study in laboratories here on Earth are in the CERN Large Hadron Collider. But the highest energy particles that we detect from outer space are millions of times more energetic than this. To think about where we might find particles of even more energy than what could come from the remnants of massive stars, we look outside of the galaxy and consider the hearts of distant galaxies themselves. Most galaxies have a supermassive black hole at the center. And as gas swirls around these black holes, as like water going down, spiraling down a drain, sometimes some of the gas is launched from above the top and bottom of the black hole in a giant geyser-like fountain that can extend longer than the size of the whole galaxy. And when some particles escape from this fountain, like mist from a water fountain, they begin to follow the magnetic field lines of the galaxy. And so cosmic rays can reach us from jets from distant galaxies. But now once a cosmic ray reaches Earth, because it's been winding around magnetic fields, it's not going in the same direction that it started in. And so you can't just look back at the galaxy or neutron star that launched it. And to make it even harder to interpret, our atmosphere blocks cosmic rays. When one of these charged particles hits the atmosphere, it collides with the molecules of air, and this collision produces more high-energy particles, which, and this is sort of what I've drawn in the cartoon there, which collide with more particles, which produce a cascading menagerie of high-energy protons and pions and muons and gamma rays and electrons and antimatter electrons, like a series of toppling dominoes. The original particle never reaches the ground. So why not study these particles with satellites in outer space? The International Space Station does have some cosmic ray detectors, but these are good for studying lower energy cosmic rays, which are more common. To think about studying a rain of cosmic ray particles, some of which are very rare, imagine collecting raindrops in a bucket. you could put out a bucket in the lightly falling rain and measure how long it takes for just one drop to land. If you had a bigger bucket, you won't have to wait as long. Now, if you had a collector the size of Caltech, you would get one of these fast-pitch baseball energy cosmic rays in that area every year. So if we want to collect enough of them to study them, we would need a really, really big detector. And that's difficult to launch into space. It's much easier to build big things on Earth. It's actually easier to build anything on Earth. And so we have to study these from the ground, which means we have to watch the atmosphere for signs that a cosmic ray has hit it. Out of all those particles produced in that cascade, there are a few different kinds that reach the ground, and so there are a few different ways to do this. I'm going to talk about using radio waves. All of the charged particles in the collision radiate light. And while the light that you see is about the wavelength of viruses, and the light that does the cooking in your microwave oven is a few inches long, I'm studying these events in light with wavelengths about the size of a car, in low-frequency radio waves, just below the FM radio band. And if you put a bunch of antennas out in the desert, as we've done here, cosmic rays will appear as a very brief flash. We're trying to do this in the Owens Valley Radio Observatory, which is about 200 miles north of here in the remote eastern Sierra Desert, just east of the Sierra. Now, the flash of radio waves that comes from this collision only lasts 10 nanoseconds. And so in order to see it, or rather sense it with a radio telescope, you have to make measurements so fast that from hundreds of antennas, we get 140 gigabytes per second. And this is more data arriving faster than what we can put into our computers. And so we have to find the cosmic ray while it happens, and then only save a snapshot of data. We use special signal processing boards to do a bunch of calculations that look for something that looks like a cosmic ray. There's one more catch. Cosmic rays aren't the only things that make flashes of radio waves. Turns out that people's electronics, electric fences, faulty power lines, welding equipment, reflections off airplanes, television stations, and more also makes brief flashes. With this telescope, we expect about 5 cosmic rays every day, and there are hundreds of background sources every second. So the calculations that we do on the special signal processing boards also have to make a decision about what looks like a cosmic ray versus background event. But then in the end, we save a snapshot of data for a window of time around the most promising events. And then what we get is the intensity of the pulse and when it happened for every antenna in the array. Now, it would be nice if we could collect everything that happened in that cascading particle shower, trace back all the particles back to the ones that they came from, and trace those back to the original cosmic ray, and then trace that cosmic ray along all the magnetic field lines back to its starting point. But we can't do that. We have to learn something about the starting point just from this summary pulse of radio waves at the end point of this journey. And we can actually do that by the energies in the pulses and the times they arrived at the different antennas. We can tell where in the atmosphere the cascade came from, and we can tell how much energy it had. And that helps us learn about what kinds of particles these cosmic rays are. And that gives us clues about some of the extremely intense environments that they come from. And so even though we can't catch a cosmic ray in a bucket, and we can't even take a photograph of it, we can learn about the dramatic environments that they come from.